So we're going to look at partial fraction decomposition again, okay? And once again, if we have something like this, 3 over x plus 2, or x plus 5, whoops, x plus 5 plus 2 over x minus 3, okay? That's equal to, I would need to get a common denominator, so I need to multiply this first fraction by x minus 3 over x minus 3. So 3 over x plus 5 times, and then x minus 3 over x minus 3, and then plus 2 over x minus 3. And I would need to multiply top and bottom by x plus 5 over x plus 5. So x plus 5 over x plus 5. And so this becomes 3 times x minus 3 over, and it's be x plus 5 times x minus 3 plus, and then this would be 2 times x plus 5 times x minus 3 times x plus 5. And now we have a common denominator, so I can add the numerators together. So this becomes 3 times x minus 3 plus 2 times x plus 5 all over x plus 5 times x minus 3. Cleaning this up a little bit more, we would have 3x minus 9 plus 2x plus 10 all over x plus 5 times x minus 3. And so that would be x squared plus 2x minus 15, combining like terms in the top, and we wind up with 5x plus 1 over x squared plus 2x minus 5. Now, what this all means, so the reason I did this is because what this means is this is equal to this, which 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 is equal to this. This and this are the same thing. So what we're gonna do today is we're going to try to integrate this. So if we try to integrate 5x plus 1 over x squared plus 2x minus 5, and then we need our dx, right? What this allows us to do is, if we know what this is broken up into, right, we can write this and take the integral of, instead of this, we can replace it with this. So this, we're going to integrate, and we would need parentheses here, 3 over x plus 5, and then plus 2 over x minus 3, and then dx. And this is a heck of an easier one to integrate. Let me slide it up a little bit. This is much easier to integrate than this one. Okay, so we're going to swap this out with this, and then we're going to be able to integrate, because really this is going to be natural log. We're going to do a use substitution and use natural log, and wind up with the integral of these. Okay, a few things to remember. All right, if we have something like this, if we have non-like factors, so something like this, if we have x plus, like we had up here, x plus 5 times x minus 3, remember that's going to have to be a fraction with one denominator, x plus 5, and another denominator, x minus 3. Okay, if we have something like this, we have x repeated factors like x plus 5, let's say squared times x minus 3. Okay, so on something like this, we'd have to have the single factor of x plus 5, plus we'd also have to have the repeated factor x plus 5 squared, and then we'd have to have the single factor. So we got to work our way up. We have the denominator with the power of 1 and also a denominator power 2, because we really don't know what our denominator is. Okay, so we got to do all the possibilities. Sometimes these numerators will come out to be 0. Okay, if that's the case, then we don't have to include it. All right, and then this would be x minus 3. So something really ugly that I would never give you, all right, but it can happen, all right, it can happen, is what if we had something like this, x plus 5 cubed times like something x minus 3 squared. Okay, so that would mean I would need an x plus 5 for a denominator plus, and then I'd have a second fraction with x plus 5 squared, and I'd have a third fraction with x plus 5 cubed plus a fourth fraction with the single one, x minus 3, plus, and then the double one, x minus 3 squared, because we don't know which one. We know we have a denominator of x minus 3, but we don't know if it's just simply x minus 3 or if it's x minus 3 squared. Okay, so that's how you'd break it up if you have repeated factors. Like you got to work your way up with the powers, like a power of 1, power of 2, power of 3, this one power of 1, power of 2, until you get to the one that you actually have in our denominator. Okay, all right. Let's do one practice of partial fraction decomposition, and then we'll start using it to integrate. Okay, so we want to write negative x plus 16 over x squared plus 3x minus 10 as a sum of rational functions, right? So we're going to need to factor this. So when we factor this, we need to think about two numbers that multiply together to give you negative 10, add to give you 3. So that'd be positive 5 and negative 2. So this negative x plus 16 over, and the would become x plus 5 times x minus 2. And okay, so there's only single factors, so we're going to write a over x plus 5 and then plus b over x minus 2. And then what we're going to do is now mentally, or I'm going to do this mentally, all right? We want to get rid of the denominators of all the denominators. We want to clear them out. So we're going to multiply by x plus 5 and x minus 2. That's going to get rid of both these in this denominator, and we just be left with the numerator. So negative x plus 16 equals, when I multiply this by x plus 5 and x minus 2, my x plus 5s are going to cancel, and I'd be left with a times x minus 2, and then plus b. And when I multiply this fraction by x plus 5 and x minus 2, my x minus 2s would cancel, and I'd have b times x plus 5. Okay, so now what we need to do is we need to make one of these drop out and become 0, because then we're going to be able to solve. So we're going to let x equal 2. Now we'll get rid of this a. So we're going to let x equal 2. And we want to do this as quickly as possible. So this is going to be negative 2 plus 16. So that's going to be 14 is equal to, well, that would be a times 0. So we don't need to write it. And this would be b times 7. So all we need to do is divide both sides by 7. And I wind up with b equaling 2. Okay, over here, we're going to let x equal negative 5. And that's going to cause this one to drop out. So if x is negative 5, let's write that. Let x equal negative 5. And so when we put negative 5 in here, that's going to cause us to be positive 5 plus 16, which is 21, equals, and when we put negative 5 in here, that'd be negative 5 minus 2. That's going to be negative 7. So there's going to be a times negative 7. And this one's going to be 0. So when I multiply it by b, it's just going to be 0. All right. So then what happens is a winds up being equal to negative 3. So what that means is negative x plus 16 over x plus 5 times x minus 2 is exactly the same as my b, which is 2 over, well, I could do, so negative 3 over x plus 5. You could write it like this, negative 3 over x plus 5, and then plus your b, which is 2 over x minus 2. Now, another way you could write this is, because this one's negative, and that's what I started to write it this way, okay, is you could write this one first, and you could write this as 2 over x minus 2, and then minus, and then this becomes a 3. So we basically drop the negative down, and we make it a subtraction. So minus, and then 3 over x plus 5. And that way your numerators will be positive, okay? All right. All right. Now, one big thing is we want to do this. We want to use this. We don't want to always use it when we see a fraction. We want to do this because notice what we started with. We started with a power okay, or it's called the degree of the polynomial. The degree in the denominator was higher than the degree in the numerator. And that's when we want to use this partial fraction decomposition, okay? So let me put a little asterisk right here, okay? So we don't want to always use this. We want to use this, okay? Use partial fractional decomposition when the degree of the denominator is higher than the degree in the numerator. In other words, remember, degree is the highest power. The highest power in the denominator needs to be larger than the highest power in the numerator, the top. Okay, and that's what we have here, because this is a power of 1 and this is x squared. So this is where we would use partial fractional decomposition. Okay. All right, let's do a problem with integration now. All right, so we want to take the integral of 9x minus 15 over x squared minus 3x dx. And again, notice this power, which is the degree 2, that's larger than the degree of the numerator. So this is a perfect example of when we would want to use partial fraction decomposition. Okay, so the denominator here factors into x times x minus 3. So this becomes 9x minus 15 over x times x minus 3. That would equal a over x, and then plus b over x minus 3. And then we're going to multiply to clear out our denominators. So we're going to be left with this 9x minus 15 equals, when I multiply this first fraction by x times x minus 3, the x's are going to cancel, and I'd be left with a times x minus 3. And when I multiply this second fraction by x and x minus 3, the x minus 3's will cancel, and I'll be left with bx, b times x. All right. So to get the b, we're going to let x equal 3. And so if x equals 3, this would be 27 minus 15. That would give you 12 is equal to a times 0, so that we don't need to write that, and then b times 3, which tells us that b is equal to 4. And then to get the a, we're going to let x equal 0. And if x was 0, then we wind up with negative 15 is equal to a times, and if x is 0, then this would be negative 3, and this would be 0, and this one's going to drop out. So we're going to be left with a times negative 3, which means if we divide both sides by negative 3, a is 5. All right, so this whole thing boils down to this. All right, so we're going to integrate 9x minus 15 over x squared minus 3x dx by letting this equal the integral of, and the first one is going to be my a, which is 5. So this is going to be 5 over x plus, and then b, which is 4 over x minus 3. And we really don't have to have the parentheses, because when you look to integrate, you're looking for whatever's in between the integral symbol and your dx. Okay, you can put parentheses to emphasize it, but you really don't have to. Okay, so how are we going to integrate this? Well, there's a sum here, right? So we can integrate each one individually. So that means this is equivalent to the integral of 5 over x dx, and then plus the integral of 4 over x minus 3 dx. Okay, we can bring the 5 out because it's a constant, and we have 5 times the integral of 1 over x dx plus, we bring the 4 out on this one. And at the same time, I'm going to let u be x minus 3. So you could do this mentally too. So u is x minus 3, which means du would equal dx. Okay, so then that I brought the 4 out, so now it's a 1, and then this denominator is my u, and then the dx is my du. Okay, some people can just do this in their head without doing the integration by substitution, which is absolutely fine. Okay, all right, so what happens is we notice, okay, the antiderivative of 1 over x is natural log of the absolute value of x. So this is equal to 5 ln of the absolute value of x plus, same thing here, but it's absolute value of u. So plus 4 ln the absolute value of u, and then plus some constant c. And we're asking for the antiderivative, right? Basically, that's what we're asking for, the indefinite integral. Then that means I got to switch this back. So instead of writing u, I need it with x's. So the u gets replaced with this x minus 3. So we wind up with 5 ln of the absolute value of x plus 4 ln the absolute value of x minus 3 plus c. And that's a perfectly valid answer, okay? That's a perfectly good answer. However, all right, we can use some logarithm properties to write this different ways. So this is a good answer, okay? But one of the properties that we can use is this. Whenever you see a number times ln of x, you can always rewrite that as ln of x, the argument of the logarithm, raised to the a power. So that means here, this one, we could rewrite as ln of the absolute value of x raised to the 5th power. And this one we could raise to the 4th power, so plus ln absolute value of x minus 3 raised to the 4th power plus c. So that's another valid answer, okay? But there's even another logarithm property that we could use here, okay? And that is when you're adding two logarithms, okay? So if we ever see the natural log of a plus the natural log of b, that's equivalent to the natural log of a times b. Right? That's something we learn in Algebra 2, Pre-Calculus, Honors Math 3, okay? So that means because we're adding here, right, these two things, these two arguments of our logarithms can be rewritten as a product. So we can write this a third way as just a single logarithm, natural log of the absolute value of x raised to the 5th times the absolute value of x minus 3 raised to the 4th. Close that parenthesis for the argument, and then plus c. And so I just want to make sure that, you know, on like the AP exam, all right, this might be one of the answers, right? Like, especially in multiple choice. In the free response, all three of these would count as being correct, all right? But in the multiple choice, you may not see this first one. You may see this one or this one instead, all right? So you got to be aware of the different ways we can write our answers. And that's just using the logarithm properties. Okay. All right. Let's do another problem now. Okay. So look at this problem. It looks very similar to the last one. However, if you inspect it, right, the degree here is not larger than the degree up here. They actually have the same degree, right? So this problem is not a candidate for partial fraction decomposition. I wouldn't use it yet. Okay. What we can do, all right, when the numerator power is larger, right, when the degree is larger or the same, what we want to do is we want to do long division, okay? So we want to divide by this polynomial. Now this is missing a term, a 0 term, okay? So I'm going to do an area model to do the division with this, okay? All right, so we are going to divide, and I like to put what I'm dividing by on the side. So we have x squared and then minus 6x and then plus 0. And I'm going to do my first column here. Okay, we're going to have 3 entries here. Okay, Now this needs to be 2x squared, right? Because I have 2x squared here. So now you ask yourself, okay, what x squared times what will give you the 2x squared? And it would be 2. And so then since this is 2 and this is negative 6x, this area for here makes negative 12x. And then 2 times 0 is 0. Okay, we're going to drop our next column. All right. And okay, so this diagonal right here needs to add up to give you this negative 10x. Okay, so for this to be negative 10x, this would need to be positive 2x. Okay, well, there isn't anything we can multiply x squared to get 2x, right? And then this diagonal right here, this is our constant one, right? Then that means this needs to be negative 6. So this has to be minus 6. And what happens is this is my remainder right here. Okay, so what this means is that the integral of 2x squared minus 10x minus 6 over x squared minus 6x dx can be rewritten as the integral of, and this is my quotient and this is my remainder. So my remainder always goes over what I'm dividing by, in this case, x squared minus 6. So this is going to be 2 plus, and we take 2x minus 6 and divide that by the x squared minus 6x. And then we need to write our dx. All right, because this is a sum, we can integrate each one individually. So this becomes the integral of 2 dx plus the integral of 2x minus 6 over x squared minus 6x dx. And you may think, okay, well now, all right, now we have a power, right, that is higher, or a degree of the denominator is larger than the degree in the numerator, and we could use partial fraction decomposition. And I would absolutely agree with you. Yeah, you could do it that way. All right. But sometimes it's faster if we just notice something, right? So notice that if we let this be u, x squared minus 6x, this is our derivative, right? So you got to notice that though, and that's subtle, right? So we got to let u equal x squared minus 6x, and this is going to make the problem faster than if we had to do partial fraction decomposition, okay? So this is just a special case where we wouldn't have to use it because we notice that the derivative of the denominator is the numerator, all right? So du is 2x minus 6, and then dx, right? Okay, so what that means is now I can rewrite this as the integral of 2 dx plus the integral of, well, this along with this become my du, right? And this is my u, so this is just 1 over u times du. Okay, so what's the integral of a constant? 2. Well, that would just be 2x plus, and the integral of 1 over u would be the natural log of the absolute value of u plus some constant c. And then switching this u back into x squared minus 6x, we get 2x plus ln of the absolute value of x squared minus 6x. All right, and then plus c. And that's the answer to this integral. Okay. All right. And that's how you integrate with partial fraction decomposition. Basically, you break it up. Okay. We only did one problem really with partial fraction decomposition. I mean, you could have done partial fraction decomposition with this one. It's just quicker if you did. You notice it's an integration by substitution. Okay. All right, guys, that's it. See you later.